This video is going to be an exercise in small parts, smaller than I usually work on, but something that I enjoy a good challenge in. This was sent by James Condon from a 1960s era generator he's working on. The machine he has is missing the main, I believe it's the main jet metering needle, so there's no way to adjust the mixture, but it's a needle that he's not able to find a replacement for. This one is the closest fit that he can get, but this bottoms out in the threaded section before the needle makes contact or sufficient contact with the jet to actually meter the fuel and therefore the ratio. So the machine is running too rich. While this one might be able to be modified in theory by turning down this end of the threaded section to allow for a longer taper on the left end of the part, work holding would be challenging, and this is not a readily available needle in itself, so I would hate to modify it and find out that we went the wrong direction. So my hope is to make at least one of these, ideally multiple with a few different ratios of needle length to threaded section length. We don't know exactly what the length of the needle should be. You don't necessarily know where the thread section will end up before it bottoms out to get the right mixture. James's estimate is that the threaded section maybe should be shortened or moved to the right about 1/4 of an inch. So we'll start with that. If that goes well enough, make a few variants that are 1/16 of an inch longer or shorter from there to give a few options. This has some challenges. I expect to work with either brass or bronze that I have on hand. The biggest challenge is going to be cutting that thread. Both of my lathes are inch-based machines. I don't know if I have a transposing gear for either of them. This is a very fine thread. Expect it's something I can't cut. That's not going to have a direct or close enough inch equivalent. The taper itself is a challenge. It's such a thin part and small taper. It could deflect as we're trying to cut the taper. I can use a very sharp high-speed steel tool to hopefully reduce the amount of tool pressure and deflection. How to set up and cut the taper will be interesting. I don't know how we might hold this to set the compound to the right angle, or try to measure this included angle and set it up based off of a measurement. Order of operations would then basically working from left to right as this is here. So cutting the taper, the threads, the secondary taper to join the two, and then either knurling it or parting it off and cutting a slot in the end. Most options for work holding this at the mill would end up damaging the threads because it's such a fine thread and I'm expecting it to be a soft material. Putting it in a V-block with a set screw that clamps it would end up damaging the threads. The other thing is going to be this spring, which helps hold the part in adjustment by keeping the threads preloaded. I need to have the overall length from the threaded, the bottom of the threaded area to the shoulder be correct for this spring or one like it. A spring might have to be selected that compresses the right amount in the available space that, when it's set right. So I'm not going to worry about that. That's going to be a second or third priority versus getting a needle that can do the job. So first thing will be to figure out what the thread is and some of the diameters and length involved here. Maybe create a rough sketch and then see if we can cut this thread and then see if we can cut the taper and then put it all together. All right, we've got a very fiddly shot here. Zoomed in about 3.5 times on the camera zoom, plus looking through a magnifying visor. So I've got the screw lined up next to a 30-second scale. And what we want to do is count the largest number of threads where we can find two that line up with the hash mark on the scale. So if we look at, we've got the 8 hash mark, so just to the left of it will be the 7. That thread is basically lined up perfectly. And if we look to the left until we find the next one that's lined up perfectly, I think it's at the 2. Yeah, so from the 2 to the 7. So if we count how many threads that is, 7, 8. 8 threads over 5 30-seconds of an inch. I do have a thread gauge. I have inch and metric thread gauges. None of the leafs fully set in here. I think my 0.5 millimeter thread pitch one was closest, but it wouldn't set in all the way. The last tooth on there, I think, is misformed or damaged slightly. If I line this up, as you can see, that sits pretty well, but not all the way in, because that last tooth on the leaf. I think we're looking at 0.5 millimeter thread pitch. Across the threads, Comes out at 4.9 millimeters. On the unthreaded portion, it's nominally 5 millimeters. I believe the tops of the threads are slightly flattened, and the threaded section is reduced slightly from the unthreaded section. That's where that 0.1 of a millimeter, couple thou, is lost between here and over here. You can just barely see that there is a step in it where it was either turned down or filed down to clean up the threads and to remove the sharp peaks. So I think we're nominally looking at a 5 millimeter by 0.5 millimeter thread pitch. That's not a standard. 0.8 millimeter is the only standard for 5 millimeter fasteners. So I can see about tracking down a die for this, but I'm starting to get some other ideas about how we might cut this thread. Specifically, I'm thinking we might be able to use this tap. This is a M8 by 0.5 millimeter tap. We can use this as a forming tool in the lathe if I can get close to 0.5 millimeter thread pitch. Because to use this as a threading tool, let's say this is the part and this is how I want to cut the threads. You feed this in along the part while this is spinning and form the threads on. But you need to feed the tool in at the same thread pitch. To turn a 0.5 millimeter thread pitch thread, I would need my carriage to move 19.5 thousandths per revolution. It's more like 19.65 thousandths per revolution. We'll see that ends up being about 50.5 threads per inch, which is of course not anything standard. So we'll look at what the Chipmaster can do. We're looking for something around 51. We can see that this is 48, this is 56 threads per inch, but we notice that it skips HB7. Let's find out what HB7 does and how close that gets us. To lay this out for this test, we're in H for the timing belt drive, high speed on the spindle, mid-range, right-hand threads, and then on this tumbler we are on position 7. I have a dial indicator zeroed out against the tool post, and to figure out when we go one full rotation, I have a pencil which is currently pointing right at the J in Jacobs. So let's go one full rotation and see how far that gets us. Hoping for 19.6 or 0.7 thou. So there we are right at the hook of the J. Almost exactly 19 thousandths. Without a tenths indicator, I can't tell more. So we're probably within about 0.5 thousandth of the feed rate we need. We're only going to end up cutting probably 5 or 6 threads in the finished part. The fewer we do, the less the tap will impact the already formed threads. The error will accumulate the more we feed it in. As this end is cutting new threads or forming the last of the threads feeding to the left, if we were feeding in really far, that 0.6, that 10 thousandths per revolution would start to accumulate a larger error by over here, where these threads on the tap would start to bulldoze and erode the already formed threads in the part. But if we are only doing 5 or 6 threads, that's only going to be about, 2.5 to 3 thousandths of error. So depending on the fitment of this part, we may get away with some slightly misformed threads. So if that doesn't work, then the option would be to track down a die that is for this, or an adjustable die for 4 or 4.5 millimeters, if we can find that in 0.5 millimeter thread pitch, and adjust it to accept this. But threading with a die up to this shoulder will be tricky. So I think our best bet is forming threads with a tap. Looking at the end of the tap, we're going to actually be running it backwards. This is not a cutting edge, but this is the back edge of that flute if it was cutting in the normal forward direction. So we're doing a forming operation where the threads down here are going to be raising and rolling the material up rather than cutting threads. However, it can't hurt to have it oriented such that if this edge does cut, we have a bit of clearance here. All right, I think we're ready for a test cut. I'm going to use a little bit of WD-40, and I'm going to be using the start and stop inputs to the VFD to stop and reverse the thread. We're not on the threading chart. We have no idea whether we can rely on the threading dial to start and stop in the right place. So we're going to leave the half nuts engaged for the whole thing, which is there. So I'm going to go ahead and start this in reverse with the spindle engaged. We're going to back up a little bit. Alright, so that's how we're going to start and stop, just with the VFD. I'm going to go ahead and dial in what should be a couple thousand step the cut for a first scratch here. And then let's see what happens. Alright, I'm going to back out, because if there's any lost motion in the half nuts or the drive screw or the lead screw or anything, this is a fine enough thread that dragging the tool backwards to the work with that backlash could damage the thread. So I'm going to bring the cross slide out, back up, dial back into where I was, plus another 5 thou. Threads look fully formed, and of course they line up because the tap indicates the timing of the thread. So I think we have a solution. Try this on the back side. You can see the silhouette of the thread looks fully formed, and on the front side you can see that it meshes really nicely with this part, and it looks fully formed. Better than I was expecting. I thought that the back of the tap was going to start to damage the threads that were formed first, but this looks really quite good. Let's try and make a quick sleeve, like a split collar, to allow us to hold the original in the chuck. That way we can align the tailstock for a matching taper, or close enough taper. And the major diameter of that part was 5 millimeters, 4.8, 4.95. So let me go see what we got for drills. So to set up the lathe to cut the primary taper, off camera I made this fixture that holds the needle with a set screw. I've got a little wad of paper in the bottom of that so it doesn't damage the threads. And then we should be able to hold this concentric in the collet chuck and dial in the compound angle off of the needle. A little unexpectedly, it looks like the needle is not concentric with the 5 millimeter shaft, even though the fixture and that hole are concentric with the chuck, and the needle 5 millimeter threaded portion is a nice snug fit in that hole. Turn this by hand, I see about 30, call it 34 thou of run out. So what I'm thinking we do is split the difference, try and get any deviation oriented vertically, since I'm measuring off the 3 o'clock position here to set the taper. So I'm going to bring this to 17, and if I go 180 degrees from here, we'll see if it's still about 17 on the other side. And it is within 1 or 2 thou. So that means that whatever deviation there is oriented vertically, and therefore we can indicate off the taper and still get pretty close to this. So I spent a few minutes adjusting the compound and setting this up to the taper. In the inner portion of this, I'm getting very little movement right here with the compound set to 5 degrees. And then down here, I get a slight deviation. I don't know if that's just wear in the needle or maybe a slight bend at the tip. But I think 5 degrees is looking, it's nominally 5 degrees. I don't think this is going to be critical, given the fact that this is, the whole point of this is to meter the amount of fuel and be adjustable. So this will give the desired range of adjustability, even if it is only nominally 5 degrees. Going to take a test cut to see if we can get a fine point taper on this piece. This is too long to be the final part, but we'll see if we can get a fine needle that looks about right here. And then, if so, we'll work it back. We're going to have no problem cutting a taper to such a fine point, even with this much stick out for the diameter. We're not down to the fine point yet. I'd have to look at the tip and see how fine it even has to be. So we'll sketch up what we want our geometry to be and then take a crack at this. So the mission on all this is to swap thread length for primary needle angle length. Right now, this front section is, let's call it 7/16 to the threads. And then the threads are 1/4 inch and the unthreaded portion is 1/8. Our goal would be, and I guess I didn't sketch the angle in close, would be for this angle to come back perhaps to where the threads currently end, more or less. You know, as if it was on this existing one, in theory we could turn that down and just extend the primary angle. If we want to go a full 1/4 inch longer, which is quite a bit, that's 7/16 versus another 4/16. So what we're looking to do, we want to keep the same thread length and unthreaded section, just so the same spring might fit. So we could do 1/8, 1/4, and we'll call it the secondary bevel or angle here. And then we've got, and I don't know what angle that's going to be. And then we've got a very long 5 degree included angle here. Then from here to the end, it's going to be 11/16. That does seem a little long. I mean, I guess we can do this. If it goes well, we'll make a second one. And we'll split the difference on the second one, do 1/8 of an inch pushback on everything. So I think that's what we'll do. We'll go for 11/16 and then the same amount of threads and unthreaded portion up to the shoulder. As it happens, turning this taper back puts us in a pretty good spot to start this one. Alright, where does that put us? We are sneaking up on 11/16. Let's turn this down to our 5mm. Yeah, we're just shy. So let's get this to 5mm. We are currently at 8.1. Right on 5.00. Looks like about the 3/8 we want for the other features up here. Just a little less. It's probably fine. Yeah, if we clean that shoulder up, there's a bit of a step there, so we'll clean the shoulder up. That'll bring us just up to 3/8 for the threads. We'll do one last finish pass on the taper, and then threading on the 5mm. We'll also clean up that shoulder before we do the threading. Alright, so I'm going to turn this in until I make contact. I'm going to treat that as my 0. Back out, and then we'll thread this in 40 thou, 20 thou depth, 40 thou on the dial. Making sure we're set up right. HB7. Interesting, we're still expanded out past the original starting diameter. So I wonder if we're fully formed or if we just like swaged material out. I decided a couple things. So I mean there are formulas of course in the machinery's handbook to figure out what the sizes of everything should be here, but it's impractical for me to measure like the root of the thread, and I'd want to sand down the top of the thread to try and get a measurement. Ideally what I would have done is use an M3 by 0.5 millimeter tap to internally thread a hole that should accept the original needle, see what that fit feels like, and then turn this one to fit. And if I make another one, maybe I'll do it that way. I can't do that now because if I take this out of the lathe, I'll lose my timing on the threads and I can't revisit it without, I mean, retiming a thread this small will be very difficult. So instead what I'm going to do is I'm going to use some 500 grit sanding belt here to clean up the tops of the thread, take the sharp edge off until the outside diameter of this measures either 5 millimeters or 4.9. Then I'll take a cleanup pass. Then I'll look at what the thread form looks like under magnification and decide whether to keep going or whether it's good enough. Alright, I think we're going to leave it there. It's measuring 5 millimeters. It's going to be a little tight. James can sand it if he wants. I'm going to make probably another one or two of these before I mail this one because this is going pretty well. On the next one, I'm going to turn this diameter down to 4.8 millimeters because clearly the tap is flowing this softer material out and expanding it, and I'm chasing my tail on that without wanting to go too far. So on the next one, we're going to make it 4.8 millimeters and expect this to flow the material out, and that matches kind of what we saw in the original as well. Is that it's 5 millimeters nominally right up against the shoulder, but there is a reduced section where it's threaded. So I don't know if they formed the threads and then took a cleanup pass, and that's why the tops of those threads are a little flat also, or if they undersized it and then turned the threads on, you know, with whichever forming or cutting process. There we go. So I'm going to use this just to clean that face up. All right. So we're all cleaned up and ready to go. I think we're done for now. I made a second one off camera. The order of operations were the same. It did go much faster being all set up for everything on the second time around. The main thing I did differently is I did undersize this diameter. I turned it to 5 millimeters. There's a slight step right here. Then I turned the last of it here down to 4.8 and then formed the threads. And that went a lot smoother. I do think that the tap is acting, it's flowing or swaging a little bit of material up into the threads as much as it's cutting down. So that came out to like 4.95 millimeters outside diameter on the crest of the threads. I think that's going to be fine, and they can always be sanded down if it's a little too tight. The knurling came out a little bit different, but it's going to serve the purpose just fine. So overall, we've got just under 3/8 inch of taper on the original. Their initial goal was to add a 1/4 inch on top of that. So we've got 11/16 of taper on the first one that was made, and this one ends up kind of in the middle. This is just under 1/2 inch. It's pretty close to 7/16. couple other thoughts during editing. I originally said I didn't have a way to hold it at the mill to slit the head without damaging the threads, but I did end up making that fixture to hold it in the collet chuck, which would have worked for that purpose. However, the other thing is that the knurls came out good enough and positive enough that I didn't need to slit it. The size is not an issue, and the slot for the slotted screwdriver would have ideally been pretty slim, and I don't think I have a slitting saw available that is that thin. Overall, I'm not crazy about using the tap this way. I think the only reason this worked at all is because of how soft the material was, and the fact that the tap that I had was M8, which is a very thick, very large diameter tap for such a fine thread pitch. If the tap had been less rigid, or if the material had been harder, I don't think this would have worked pretty much at all. Well, we're back. James tried the parts out. They threaded in and overall seemed like a good fit. However, the needle did end up being too fat up towards the threaded section. The hole at the top of the carburetor body, but below the threads, could only accept a needle up to a certain diameter there, the root of the needle. You can see that the original one did have a smaller diameter at the top before it tapered out to where the threads are. In particular, the longer of the ones we made last time, this is in the fixture for holding it in the lathe right now, the longer of them does have a particularly wide root. So the plan is to put these back into the modified fixture. This is the fixture we used last time for holding the parts to clean up the head as well as to line the taper up on the original part. I made some changes to it to see if we could hold these again. I counterbored each end, well, this end for the head, the thumb screw, to sit a little lower, and this end the rest of the way to expose the root of the taper. The plan will be to measure the largest diameter of the primary taper on this part, and then hold these one at a time and reduce down to that diameter, however far down the taper we have to come, so it can fit into the carb body. James also sent this other carburetor needle from another carburetor in this that was used on the same series of Honda generators, or the larger siblings to the one in question. You can see the threads are smaller. They're nominally 4 millimeters in diameter. The needle is shorter, and the thread pitch is more coarse. I measured this, and it comes out to nominally 4 millimeters major diameter and 0.75 millimeters thread pitch, which is not a standard, just like the other one. Here's a thread gauge that has most of the common pitch and diameter combinations on it. We can see 4 millimeter would normally be 0.7 or 0.5. However, this is confirmed to be 0.75 based on my thread gauges. So that is just another data point in what kind of considerations there might be for what this carburetor would be. However, we know from the fact that this one threads in that it is the right thread. You know, these, even the shorter of these, did start threading in until the taper bottomed out because it was too wide. This is another good data point to have on this one. It does look like it's the same or very, very close taper. I don't think we're going to change anything on the included angle. It's 10 degree included angle, 5 degrees off axis on each side. So I don't see a reason to remake these, but I think we will reduce these diameters on the taper down and get these back in the mail. So let's get over to the lathe. We'll see if we can get this running true enough with as little support as this has now, because it's thinned out in the middle. We'll see if this is going to hold true enough, or if we have to somehow shim behind opposite the screw to try and get this centered up well, or maybe just make a whole new fixture that gives us a better hold. If this reduced diameter is not perfectly concentric, it's not the end of the world. We'll undersize it a little bit if we need to. That'll make up for the fact that it might be non-concentric with the axis of this screwing in. I measured the root of the taper on the first needle that James sent, and it measures right on 2.5 millimeters. So that's just a thou or two under 0.1 inches. So we will bring the base of these tapers in, starting with the bigger one, to measure a thou or two under 0.1 inches. As you can see, we do have some run out or concentricity error. I think that's from the couple thou of space there is between the needle and the fixture. I'm really not too worried about it for turning further up the taper and bringing this into diameter. I don't think it's worth making a new fixture over, but we'll see how this cut goes, and if there's a visible error that bothers me, maybe we'll revisit. Alright, put the next needle in. This one ended up being, as far as I could tell, perfectly concentric. We would see run out at the tip if this was not aligned nicely. So this one will probably come out being a little bit nicer of the two. I also swung this one with the tool away from the chuck a little bit so we get more clearance behind the cutting edge. We should have enough clearance to get in. It's very close. We have just enough where the chuck's going to rub to get all the way into the root, or to the bottom of the thread. So we'll give that a shot. I'm going to feed it by hand, at least the first time, and we'll see how this looks. 5 thou depth of cut. So I think that's it for the second pass on these. The modification went about how I expected. The one on the left definitely came out better. The one on the right, if you look real close, it doesn't show up on camera, but if you look real close at it in person, you can see the concentricity error where the taper is not coaxial with the reduced part of the needle now. But I don't think it's going to have any operational impact. It's cosmetic only. If we do any more of these, maybe I'll be able to isolate the factors of why one's held concentrically and one's not. Either way, thanks for watching. We'll get these in the mail, and hopefully everything turns out on this go-round. And one more iteration after James got some more information from a few people that had some reference parts. We're here with a slightly different set of proportions. Of course, the same thread, but the lengths and angle of the taper are all slightly different. Overall, these use the same process, same order of operations, just different measurements, ratios. So we'll send these off and see how they go.